Hello everyone, my name is Daniel, and today I'm presenting SOAR, a synthesis approach for data science API refactoring. And SOAR is the result of joint work between Anne Sagny, currently at Yale University, Aidan Yang, which will be joining CMU this fall, and my advisors Inês Lins and Vasco Manquinho at IST, and Ruben Martins and Claire Leguez at CMU. Imagine Alex, a data scientist, wants to create a machine learning model for speech recognition. So they start writing some code using TensorFlow, one of the most popular deep learning frameworks, and they even get far enough to write some test cases. But then Alex realizes the model they are building would benefit from using PyTorch instead of TensorFlow, because they could reuse some of their old PyTorch code for this task. So if Alex wants to switch over from TensorFlow to PyTorch, do they have to start over from scratch? This is an API refactoring or migration problem, and it applies in many domains, particularly in data science. Since interest in data science has soared over the past years, many libraries have emerged, and they're still in their very active development. For instance, in this bar chart here, you can see the number of releases that three popular data science libraries have had in 2019 and 2020, and you can see that TensorFlow alone had 19. And so this is why we present SOAR, an end-to-end technique to refactor between libraries. And the idea of SOAR is that it replaces each call to a library in the original source code, in this case TensorFlow, with their corresponding call in the target library. For this example, PyTorch. SOAR is built upon three key observations, and the first is data science APIs usually have really good documentation. And to illustrate this, I have here the documentation of one of the APIs from the example I showed earlier. This is the documentation page for the TensorFlow API dense, and you can see here it has a small summary, and if we scroll down, we also have a more detailed description, and if we go further, we also have a list of parameters. And if we look at the documentation page for the corresponding API, but in PyTorch, we see the same pattern. So it also has a small summary, a list of parameters, and if we go down, we also have details regarding the shape of the input and output tensors. And so in SOAR, what we do is we leverage the detailed documentation of these libraries to automatically create mappings between the source and the target APIs. And you can see here this table on the left has the source API, and on the right we have the most likely matching API in the target library. Using the API mappings, we replace the APIs in the original source code with their corresponding targets. But unfortunately, the API mappings are only the first part of the problem, because they only get us the new method names, but say nothing about the arguments. For example, you can see here there is a mismatch between the number of arguments of the source and target APIs. TensorFlow then takes one input, but PyTorch linear, which is the corresponding API, takes two. So how can we compute these new arguments? And this leads us to our second key observation, which is that computing the arguments is a great fit for program synthesis. So what we do in SOAR is we extract information regarding the argument types and also constraints on those arguments from the documentation of the target library to enumerate possible values for each argument of the refactored APIs. And we do this on a per API basis following a generate and test approach. For example, for the first API here, SOAR would generate possible values for both x1 and x2, and then it would test them using per API tests that we generate automatically from the originally provided user test cases. And this is all possible because SOAR leverages the documentation information also for the synthesis process. Our final key observation is that well-documented APIs usually have informative error messages. So SOAR leverages the error messages generated throughout the synthesis process to add new constraints to the arguments of the refactored APIs. And this helps speed up the synthesis process by pruning the search space. For example, if we try to instantiate torch linear with a negative dimension, for example, -1, then PyTorch will output the following error message, trying to create a tensor with negative dimension -1. And so SOAR uses this error message and interprets it to create a new constraint on the first argument of torch linear. In this case, the constraint that it creates is x1 must be bigger or equal than 0. We evaluated SOAR on 40 benchmarks from 2 different domains, 20 benchmarks corresponding to migration tasks from TensorFlow to PyTorch, and 20 benchmarks from dplyr to pandas. And the second task is actually a cross-language migration because dplyr is an R library and pandas is Python. For this talk, I'll only be focusing on the TensorFlow to PyTorch results, but you can find more details regarding the second task on the paper. So for the TensorFlow to PyTorch tasks, each benchmark corresponds to migrating a neural network with between 3 and 44 layers, including some popular architectures, namely autoencoders, a family of PGGs, AlexNet, LeNet, among others. This bar chart here shows the impact of each idea I discussed throughout the talk. So the y-axis is the percentage of benchmark we solve with a timeout of an hour for each benchmark. And the x-axis corresponds to turning off a different feature of SOAR. So the first bar corresponds to turning off the documentation-based mappings. And so if we use random mappings instead of the documentation-based mappings, we cannot solve any benchmark. And this is because both PyTorch and TensorFlow are huge libraries with over 2,000 APIs each one. So it takes too long to try every combination. The second bar is a version of SOAR where we don't use the documentation for the synthesis. So in this case, we can solve 25% of the benchmarks. And the third bar is the number of benchmarks we solved without the error message understanding model. And in this case, we can solve 70%. And the fourth bar is a full approach with all features turned on, and we can solve the 80% of the benchmarks. This is a migration example, one of our benchmarks, an image autoencoder. We have the source code here on the left, and the synthesized code is on the right. And here you can see that SOAR mapped one API conv2d to 2 APIs on the right, permute followed by conv2d. And the reason we have a one-to-many mapping here is because PyTorch and TensorFlow expect slightly different arrangements on the input tensors. This one is just a simple mapping of ReLU to ReLU without arguments. So it's the simplest there is for SOAR. And finally, this is an interesting one, another interesting one, because we are doing a mapping of reshape to view, and reshape and view are somewhat different words with different meanings. So it's interesting that SOAR is able to figure out the relationship between these two APIs. So SOAR is an entirely new approach to API refactoring, and there are still some limitations and many venues for future work. One limitation is that SOAR requires intermediate outputs to be tested independently, and essentially this means that it must be possible to test each refactored API independently. Another limitation is that the error message understanding model is library specific, and because different libraries have different stylings for error presentation, it might not generalize well across libraries. A third limitation is that SOAR does not support many-to-many mappings. Our current implementation only does API mappings that are one-to-one, and we also support a limited one-to-many. Okay, to conclude, we presented a novel approach to API refactoring that requires no training data, leverages API documentation and error messages. We also guarantee that all the migrated code passes the user test cases, user provided test cases, and the approach is also language agnostic. We also provide the source code, so all the code is open source, and we also have a replication package that you can use to reproduce all of our results. And the key takeaway from this talk is that documentation can also help in API refactoring tasks. And thank you for your time.
Good afternoon again. We have Daniel Ramos from Carnegie Mellon University that is here to answer your question. We have the first one from Pascal Amusuo. And the question is, how would SOAR react if a function in TensorFlow doesn't have a corresponding function in, say, PyTorch?
Okay, so our key assumption is that it is possible to replicate behavior across libraries. So it must be possible to somehow replicate the behavior of the TensorFlow function, but in PyTorch. It doesn't have to be a one-to-one mapping. It just has to be possible to replicate that behavior, even if it's using a set of functions instead of just one.
Okay.
But in principle, it would work.
Okay. Some other question from the audience? No question? I have a question for you. It seems that SOAR produced very interesting results spending a small amount of time. So that I was wondering if you compared SOAR with some baseline approach to have a deeper understanding of the validity of your approach.
Okay, so we didn't compare against any existing approach because there is no approach that does what we do from an end-to-end. So I think the key innovation in SOAR is that we are able to actually test and prove, or at least it's a soft proof, but we can somehow provide some theoretical guarantees that the program synthesized the corresponding translation works, and it's possible to get it to actually run on an existing on an environment. And as far to the extent of our knowledge, there is no actual approach that does this, because most things are most existing work is based on either just doing mappings, API mappings, or using NLP-based approaches. And when you're using something like NLP to do code translation, it is often the case that we'll get some syntactic errors, and so the program wouldn't even compile. And so that's the reason we don't have any comparison results in the paper. So we didn't try to compare against anything.
Okay, but since you made available the tool and also the data set, you will become a baseline for comparison for
hopefully
future researcher. Okay, we have a second question from the audience. Is by Mohayemin. I'm sorry for the pronounce. And the question is your approach specialized for data science APIs, or just that you evaluated with data science APIs?
Okay, so we evaluated
a question about the generalizability of the tool.
We have a section regarding generality on the paper, and our key assumption is that it must be possible. So the answer to the question is it's not specialized for data science APIs, and it could be so it could be applied to other domains. And our key assumption is that it must be possible to compare the output of the programs in the source and in the target library. So, for instance, let's go with the data science APIs. TensorFlow and PyTorch, neural networks written in TensorFlow and in PyTorch, take as input an input tensor, which is just an n-dimensional array, and they always output another tensor, so another array. They're just matrices, right? So a neural network takes as input a tensor and outputs a tensor in TensorFlow, and in PyTorch we have the same behavior. So it also, the input to a neural network written in PyTorch is also a tensor, and it also outputs a tensor. And the tensors are very mathematical objects. They're just arrays of numbers. So it's easy to compare the outputs of programs written in TensorFlow and in PyTorch. So as long as that assumption holds, for instance, let's say for image processing, if we are doing a migration for image processing libraries, the output is always going to be an image for both the source and the target libraries. So it's possible to compare that image and say, well, these programs are equal, or they're not. And I think that answered the question, hopefully.
There are some other questions. We have 4 minutes to spend all together, so hurry up. If you don't have any question, I have another one that is mostly linked with one by Bohamian. So you mentioned in the paper, also in the presentation, and in the answer, in the previous answer, that your experiment concern deep learning library migration in Python.
Mm-hmm.
And so you realized and wrote correctly in the paper that this is elimination for your approach. Can you provide us some indication on if this limitation can be overcome? And if the answer is yes, and I suppose that is yes, can you estimate the effort to adapt your approach to work with other kind of API, with other kind of library, or maybe other kind of languages, on Python, for example?
Mm-hmm. We do also have experiments between Python and R, which are two different languages. So it's a cross-language library migration in the paper. But the effort should be minimal, as long as that key assumption that I said earlier holds, which is that it must be possible to compare the outputs of the programs in the source and target libraries. And so to adapt the code, I guess we would need to do some. We would need to adapt the code slightly to get it to work with a different library. We'd also have to somehow parse and extract the documentation from the documentation pages of the source and target libraries. And another thing that we would have to do is write an error message understanding model, because the current one is very specific to the deep learning approach. So those are the 3 key things that would have to be done. So get the documentation from the APIs, write a new error message understanding model, and slightly adapt the code. But it should be, at least shouldn't be too hard to do, because the core approach, or the approach itself, should be independent of the domain.
Mm-hmm. Okay, thank you for your answer. I don't have other question for you. So in the meantime, we have to wait for an additional question, short question, since 40 seconds left before being projected in the backstage once again for me and for you in the discussion room, where you can meet the attendee of this session, and then I hope that you will interact in a very productive fashion, so you can maybe also start some collaboration with attendee of ICSI, since this is one of the most important effects when you attend the conference. Thank you.